please.
Hi, everybody. So today I'll be talking about our work on solving the unique connectivity constraints that arise in trying to compile circuits to error-corrected
Is it fun?
Oh.
Say something?
Hello?
Okay.
Okay.
Perfect.
So yeah, like I mentioned, I'll be talking about our work on solving the unique connectivity constraints that arise in trying to compile circuits to error-corrected quantum devices. So as many of you here probably know, there's been a lot of interest in actually building quantum computers in the past couple of years from several major industry players. And the motivation behind this is some exciting applications that people see of quantum computers in the future, like Shor's algorithm for factoring large numbers, or the simulation of molecules for chemistry. But there's a roadblock on this way towards these interesting applications, which is that these large-scale applications require orders of magnitude more operations than we can directly apply to our quantum computers. Luckily, we have a solution for this problem, which is quantum error correction. So the basic idea of quantum error correction is that we use redundancy in order to drive our error rates arbitrarily low. So we encode one logical qubit using several physical qubits. One of the most popular approaches to quantum error correction is the surface code, and I've drawn a little cartoon of a surface code qubit here. This entire square patch represents one logical qubit, and each of the small circles represent a physical qubit. So the really exciting thing in the past couple of years is that we've seen physical implementations of the surface code. So we just a few years ago, we saw the first smallest scale examples of a distance 3 surface code, and then just last year, we saw a really exciting experiment out of Google where they were able to demonstrate this scaling property that I was discussing, where they created a small logical qubit and then a larger one, and noticed that the error rate did actually go down. So now that we have this hardware on the horizon, it's time to start asking the question of how we compile circuits for surface code devices, which is the focus of our work. So I showed you one of these logical qubits, and we can think of a surface code quantum device as like a plane of these logical qubits arranged in 2D. So we can represent this as a grid graph, where each of the vertices now is a logical qubit, and the edges represent pairs of logical qubits that are adjacent, but not the diagonal. So we end up with a grid graph. So given this representation of a device, let's think about how we could compile a circuit down to it. So first, we need to decide which of these logical qubits will represent the qubits that appear in our computation. So this is one example of such an assignment. And then we need to plan the execution of our 2-qubit gates. So it turns out that the way you implement a 2-qubit gate in the surface code involves finding a path between the 2 qubits that the 2-qubit gate acts on. So this is an example of a path for this particular gate. However, we cannot use 2 vertices in our graph at the same time for 2 different gates. So now we have this second gate that is logically parallel to our initial one, but it's physically blocked, so we can't execute it in the same time step. Instead, it must wait for the execution of the other gate and then execute in the next time step. On the other hand, if we had picked a slightly different arrangement of our qubits, we would be able to find a single-step execution. So our goal is to figure out how to compile our circuits while using the least number of time steps. So we call this the surface code mapping and routing problem. There are 2 inputs. On one hand, you have a circuit, which we're particularly focused on 2-qubit gates, and also the T gate, which is a single qubit gate, but it turns out that in order to implement it, you also need to do this sort of routing procedure. And then we also have some architecture that we'd like to execute the circuit on with certain distinguished vertices, which again are the routing endpoints for those T gates. And our goal is to find one of these schedules for executing the gates, and we want to minimize the number of time steps. And additionally, a small detail is that there's some constraints on the last edges of these paths. On one end, they need to be vertical, on the other end, they need to be horizontal. Okay. So our approach to this problem splits it up into 2 phases. It's an NP-complete problem, so our initial relaxation is to think about it as a mapping problem and then a routing problem. At the mapping phase, our insight is to take a dependency-aware view, so we're trying to predict which operations actually have the potential to conflict with one another. And then at the routing phase, our insight is that we want to search for the best order in which to route gates, which can perform significantly better than some fixed heuristic for gate routing order. And at both of these phases, we have a sort of unstructured discrete search that we implement via simulated annealing. So I'll start by talking about the mapping phase, which is how we're going to assign qubits in our circuit to locations on our grid graph. So one thing that you might do to solve this kind of mapping problem that we've seen in prior work is to construct something called an interaction graph. So this is a graph that corresponds to our circuit, where we introduce an edge for every pair of qubits that are involved in a 2-qubit gate. And this can give us some sense of what sorts of things should be mapped close together to avoid conflicts. But the problem occurs with certain circuits like this that have a high density of connectivity. So if we look at this circuit, we end up with a complete graph, which really gives us no information for mapping and routing. Basically, any map that we evaluate is going to be equivalent because of the symmetries in this graph. So we don't really learn anything from constructing the interaction graph. And so I think of this as analogous to like a flow-insensitive program analysis, because we're not tracking any information about when these interactions occur. On the other hand, in our work, we do have the simple extension that we call the layered interaction graph. So in this case, the first thing we do is we divide a circuit into layers of parallel operations, and then we augment the interaction graph with this information, basically. So we have a sequence of graphs now instead of just one graph. So now we have a flow-sensitive analysis. And the interesting thing we learn when we construct the layered interaction graph in this case is there's really only one pair of operations that we need to worry about. All of the other ones, there's no way to execute them in the same time step anyways because of the dependency structure of the circuit. So we really should just focus on a mapping that allows us to route these two gates in parallel. And so the way our dependency-aware mapping algorithm works is that it tries to minimize the number of conflicts. And we define a conflict as a pair of edges that we have labeled as occurring in the same layer and have overlapping bounding boxes with respect to a mapping. So let's look at an example. Here is one potential mapping of some qubits onto an architecture, and we draw the bounding boxes for each of these operations, which turned out to actually exactly coincide, so we have one conflict. On the other hand, if we choose this different mapping, the bounding boxes are now disjoint, so we have no conflicts. And it turns out that with this second mapping, we can route these gates in parallel, but with the first one, we can't. So our conflicts were able to capture that difference between these two mappings. So now I'm going to move on to talking about routing. So now that we have fixed a qubit mapping, how do we find a route for each of our gates? Well, one basic thing you would want to try is this greedy strategy, where we have some set of parallel gates, and in order to route them, we just iterate over them, find the shortest path that we can route each gate along, and then remove those vertices from our graph and continue. But there's something really interesting about this algorithm, that the order in which we iterate over the gates is going to matter. Because it's a greedy algorithm and we're changing the graph as we go, the order of iteration matters. And so the big question here is, how do we choose which order to iterate over the gates in? So just choosing some reasonable best gate first is going to give you a suboptimal result. So let's look at an example. So here we have one C0 gate and two T gates. And one reasonable heuristic that actually has some results from theory about its approximation ratio is to route the shortest gate first. So in this case, this is the shortest gate, but is the C0, but now we've blocked the two T gates from executing. On the other hand, there exists an order in which we can route the two T gates at the same time. So we should prefer this order if we can find it. And so that's why we perform a search over the possible orders. So we can do better than any fixed order by just searching over orders before committing to one. And an additional detail here is that we weigh our reward for routing a particular gate by the criticality of that gate. And that helps us avoid a long tail of operations at the end of our execution because we've been waiting on some critical gate. So now I'm going to transition into talking about our experimental results. We collected this pretty comprehensive benchmark suite of over 200 circuits, a lot of common algorithms and subroutines. So the closest related work to ours was something called AutoBraid that appeared in past work. AutoBraid did not try to route T gates, so here we're just focusing on the 2 qubit gates. And we're comparing against AutoBraid on 2 different architectures. The one on the left we call the square sparse architecture, which maybe you can see why. And then the one on the right is what we call the compact architecture. So here we're more resource constrained. This kind of represents a more near-term setting where we don't have a million qubits. And so we see on the square sparse architecture, the most common thing to happen is that AutoBraid and our approach called DASCOT find the same number of time steps. And this is because basically you can get very close to the optimal because you have a lot of routing space. But on the other hand, as we reduce the resources, there are a lot more cases, which is about 60% of them, where we find a solution that's strictly better than the one that AutoBraid finds. And our approach is especially well suited to the QFT, quantum Fourier transform circuits. And if you know a little bit about the structure of QFT, that might not be surprising based on the example I used to motivate the mapping algorithm that we use. So here we see the gap growing in the cost ratio, which is basically like the number of steps in your solution divided by the depth, which is the optimal possible solution. That's growing as the number of qubits in our QFT increases. And a final experimental result is that we developed this SAT-based optimal baseline. So this solution does not scale at all. It only works for very small circuits where we encode basically the existence of a solution with k time steps into a SAT instance. And then if we find one, we turn it into a solution. And if not, we increment k. So in this way, we find an optimal solution. And what we find is that for almost all of our benchmarks, again, the ones where the SAT-based solution actually terminated, we're able to find solutions that are very close to optimal. They're just these 5 cases at the top where we're far away. So I'll conclude here. Check out the paper for some of the things I didn't have time to talk about, like the details of our SAT encoding, and also this work has been sort of integrated into our compiler WISC, which also does some other things from other papers. So go check that out as well. Thank you.
Thank you. Questions?
Sure. Hi, that was a great talk. Thank you. So my question is a surprise. So I'm surprised that simulated annealing did so well. Okay. So what do you think is the reason, right? Because it's it's not supposed to be getting the optimal solution every time. So do you feel like that's something that will continue to be the case as you scale up, or is it like, what's your take on that? I'm just curious.
Yeah, that's an interesting question. I think that this is also saying something kind of about our the instances that we were able to find optimal solutions for. That they're very small, so you have a high probability of something like simulated annealing finding a good result. I don't necessarily expect it to continue to be this close as you scale up if we had some way of knowing the optimal. But I don't have anything better that can actually solve those large instances. So,
Thank you.
All right, thank you again.